Module 8 covers Chapter 7 in your text. This module will be separated into several small presentations. We're going to cover Lewis dot formulas for atoms and ionic bonding and then covalent bonding. We'll spend a good deal of time drawing Lewis structures for covalent compounds. And finally, we'll talk about a few things that might be new. Lewis structures should be a review for you, but formal charges and resonance and polarity may be something that you haven't seen before. So to start talking about different types of bonding, we want to think about what a chemical bond really is. And a chemical bond you should have in your mind is just an attractive force that holds the atoms together. There's no physical tether between the two atoms. So when we say chemical bond, we're just talking about the forces that are holding those two atoms together. And the electrons that are involved in this bonding are usually those that are in the valence shell only. So if you look on your periodic table, let's just take sodium for example. If you look at the electron configuration for sodium, you'll find that it's 1s2, 2s2, 2p6, 3s1. When I say valence shell, I mean the outermost shell, which is the one furthest from the nucleus, and it's this number here that tells you the size of the shell. So for sodium, the valence shell is the N equals 3 shell, because that's the shell furthest from the nucleus. So there's only one electron in the valence shell for sodium. When we talk about chemical bonds, we're focusing on two different types for now: ionic bonds and covalent bonds. An ionic bond is when you have an electron actually transferred from one atom to another. And this happens when you have an element that has a very strong attraction to the new electron and one that had a very weak attraction to the electron that it's losing. The ionic bond results in a positive ion and a negative ion since there was an electron transferred. So you have an electrostatic attraction between the two ions. Covalent bonding is different. In covalent bonding, you don't get any transfer of electrons, so you don't have any ions present. What you have instead is electrons in between the two nuclei that are being shared, so both nuclei are attracted to those electrons in between the two. There are lots of differences between ionic and covalent compounds, and these are just good general things to know. If you understand the differences between ionic and covalent compounds, it can tell you a lot about a material. So for example, looking at the melting point, we can see that usually melting points are usually ionic compounds are solids. So when you're writing equations, if you've reacted something like potassium with iodine, and you need to know whether you formed a solid, a liquid, a gas, etc., here's a big tip. Okay, potassium and iodine would make potassium iodide. That's an ionic compound, and so you could guess that it was a solid. Typically the melting points are pretty high there with 400 degrees C or higher. Covalent compounds have much lower melting points, and so some of those will be gases or liquids or solids, but they're going to be solids with low melting points. So it's going to be easy to create a liquid or even a gas with those. Think about some examples that you know. Obviously, sodium chloride is a solid, table salt. Water is a covalent compound. Ethanol, covalent compound. Carbon dioxide, that's a gas. Okay, so just thinking about some examples that you know of, that you know the state of at room temperature and pressure, can help you to remember the differences there. We can also look at solubility. So if we take a polar solvent, for example water is a polar solvent, what you will find is that ionic compounds are generally soluble in polar solvents and covalent compounds are generally insoluble. The opposite of that is true. For a nonpolar solvent, covalent compounds will be soluble, but ionic compounds will be insoluble. We can look at the conductivity as well. You're going to see for ionic compounds, they're going to be conductive in both the molten solid, kind of the lava state, and the liquid state, as well as the aqueous solution state. However, covalent compounds, you're going to see, are not conductive in either the molten solid or liquid stage, and usually not even in the aqueous phase. Sometimes they can be poor conductors in the aqueous phase, but in general you get conductivity from ionic compounds but not from covalent. And finally, just kind of a reminder, you've probably already learned this, ionic compounds we form from metals and nonmetals, and covalent compounds we normally say are nonmetals and nonmetals. Now let's think about why that would be true. In an ionic compound, you have to transfer an electron. So if we take a metal, let's just use sodium, and we look at the property called electronegativity. Electronegativity is the ability for the atom to stabilize an electron or to attract the electron to itself. So if we found something with a low electronegativity, meaning it doesn't attract the electron to itself very well, and a high electronegativity, meaning it really wants that electron, that would be the case where we could see a transfer of electron. Because the atom that has it doesn't want it that bad, and the atom that wants it is going to be able to pull it away. So sodium, if you turn to the back of your periodic table, it shows you the electronegativity on the top right. So look at sodium. The electronegativity is 0.93. Look at fluorine. The electronegativity for fluorine is 3.98. And what you'll find is on your periodic table, the trend is that electronegativity will increase in the upper right hand corner, ignoring the noble gases. So as you go across to the right and as you go up, you're going to get higher electronegativity. Okay, well think about how you separate the periodic table into metal and nonmetal. The metals are down here and the nonmetals are up here. So if that's the trend for electronegativity, your nonmetals are going to have high electronegativity, your metals are going to tend to have lower electronegativity. So combining one of each is going to give you the best chance to get an ionic compound. Covalent compounds, on the other hand, are formed from two nonmetals. All the nonmetals are close together on the periodic table, and so they're going to have similar electronegativities. Just take a look at oxygen and fluorine. Let me get some space here. On your periodic table, if you look at oxygen, oxygen has an electronegativity of 3.44. Fluorine has an electronegativity of 3.98. So if we're going to make a compound from oxygen and fluorine, here's an example, oxygen difluoride, we're going to be comparing 3.44 and 3.98. Those are very similar to one another compared to what we saw with sodium and fluorine. What that means is the fluorine wants the electron a little bit more than oxygen, but not enough to be able to pull it away. I always think in my head of this as a tug-of-war game, right? The higher the electronegativity, the more you can pull it. And if you are up against somebody who has a really low electronegativity or really low weight, you might be able to pull it completely out of their hands. So your nonmetals, their electronegativities are usually going to be too similar to be able to have a transfer of electrons.